Hi, NA Physics, it's Mr. Neff. Today let's talk about index of refraction. And before we do you know what a house wears? I'll tell you at the end of the video. Index of refraction is the idea that light travels at different speeds through different materials. Now, this seems wrong at first, right? You've heard the thing from Einstein, the second postulate of special relativity, that says that in inertial reference frames that all observers measure the same speed of light. But that's not what this is talking about. Einstein's saying that it doesn't matter how you're moving, you'll see the speed of light in a vacuum as the same as somebody else who might be moving differently than you. But what we're talking about here today is how does the speed of light actually change when it goes into a different material? And Einstein would say readily, oh yeah, when it goes into glass, it's slower. When it goes into water, it's slower than it is in air. So we say that light traveling through a vacuum is this constant speed, c. That does refer to that second postulate of special relativity. Einstein called it c because it's a constant. 3.0 times 10 to the 8th meters per second is a number that we will use for this. Some of you will be in a situation where you use more significant figures in the future. Now, we say, though, that light travels through different materials at different speeds. And it turns out that the more optically dense something is, the slower it's going to travel. So look at this nice picture. Here's a picture of a light ray coming from the left, and it's hitting some block of something. This is a piece of plastic, a piece of glass. I'm not really sure what it is, but we could figure it out based on some of these angles. And by the time we're done talking about index of refraction and Snell's law, you'll be able to do that too. Still, you can see that it's moving this way, and it has a certain wavelength frequency, and those two are going to multiply to be the speed of light, 3 times 10 to the 8th. But then it goes into this material, and because it's moving slower in the material, it gets bent like this. We call this bending refraction. The next video, I'll explain as much as I know about refraction. And it instead of going along this straight line path, no, it bends and it goes along this other path. And then that same thing happens in reverse over here. It goes back to the original fast speed, and because of that, it bends the other way. So this bending is some evidence to say that it's traveling at different speeds. Now, why would this be? Why would it travel at different speeds? Well, the way we make sense of this and what we think is going on here is there's a wavelength change. So take a look. Here comes the light traveling through the air, and it's traveling fast up here. We say that the speed up here is basically that speed of light, c. You can see that c is the product of the wavelength and the frequency, and we've seen that a million times. Wave speed is wavelength times frequency. Now, it's hard for me to show you the frequency on a still picture, but the wavelength is shown here very nicely from a crest to a crest. Remember, light is a transverse wave, and so this is drawn very, very well, and you get this size wavelength. Now, it goes into the glass, and the light is continued, the next bit of light is continued to be made from the last bit of light. Remember, Huygens' principle says that that any spot on a wave is the source for the next spot on the wave. And so the waves in the glass are being made at the same rate as they were before the glass. And so all that is to say that the frequency on this side of the interface and the frequency on this side of the interface, well, they are the same. But here's the thing. Because it's not as easy for the energy to go through the glass as it was through the air, it makes less progress in a period of time. And so you can see here when you're down in the glass, the wavelength is only that big. Can you see just by looking that the wavelength is smaller here than it was up there? And so I take that big wavelength and multiply by the frequency, I get the speed of light. Now I take this same size frequency, but I multiply by this smaller wavelength, and of course I get a velocity that's smaller than what you would normally consider the speed of light. It is the speed of light, but it's the speed of light in glass. It's not the speed of light in air or in a vacuum, which we basically say is very close to the same thing. So frequencies stay the same, wavelengths change, so speeds change. So now, based on that idea, based on that ratio of how fast the light will travel in a substance compared to how fast it would travel in a vacuum, we define a new quantity. We call it index of refraction. The symbol for it is going to be a lowercase n. And this index of refraction is what I just said. It's that ratio of the speed of light in the vacuum to the speed of light in that material. And so n, you can see, is that speed of light in a vacuum divided by the speed of light in the material. And so you're going to divide the speed of light in a vacuum, c, by the speed of light in the material. I often indicate this as v sub n, although you don't usually see that, but I know that it helps students. And so if you said, well, what does it really mean? Well, it's the number of times slower light travels in that stuff than it does in a vacuum. And so we can see a chart, something like this. And we can say, okay, well, the index of refraction for a vacuum is 1. Well, that means it travels the same in a vacuum as it does in a vacuum. For air, it's pretty much 1. And we'll just take it for granted that it's basically 1. Now, there'll be problems about water. That'll be a common one. And so you're going to see that 1.33 very, very often. You're going to see different kinds of plastic like acrylic. You're going to see glass, and of course people are interested in diamonds, and so you'll see diamond coming up in the problem. So all that is to say, what are these numbers? These numbers are the number of times slower the light will travel in that substance than it does in the vacuum. You're going to see in the next video that that amount of bending that happens at the interface, that amount of refraction, is proportional to the index of refraction of the substance you're coming from and that you're going to. And you'll see that in the next video, like I said. Hey, did you hear what the house wore? It wore a dress.